Okay, so welcome again to another lecture in our C-star algebras and groupoids course. So again, just the advertisement, but I think everyone here has already sent me an email. So thank you very much for letting me know you're interested in our mini workshop. But if anyone is listening online, then of course you're still welcome to attend our mini workshop. Just send me an email and let me know. So yeah, I'll now that we've gauged everyone's interest, we'll start actually organizing the details, and I'll let you know more about this next week. So stay tuned. Okay, so if you remember, so last week we were talking about Étale groupoids and their C-star algebras, and today we're going to talk a bit more about certain kinds of Fell bundles over Étale groupoids. So first, just a little recap. So yeah, remember last week we introduced this reduced C-star algebra, and also briefly this corresponding maximal C-star algebra that you can define from any locally compact Hausdorff-Étale groupoid. And it just consists of these complex valued functions, continuous functions on your groupoid basically, but under this convolution product. You can't quite, to get completeness, you start with these compactly supported guys and then complete with either the reduced norm or the maximal norm in order to get your C-star algebra. In particular, as a sort of toy example, we considered this groupoid, which is just it consists of basically a space. So a trivial groupoid, the complex projective space of dimension n, times this slightly not so trivial groupoid where you just have two copies of 0, 1. It's just the full equivalence relation on a set with 2 points, right? So here the product is non-trivial, here the product is trivial, but here the topology is non-trivial, whereas here the topology is trivial, it's discrete, right? So you combine these two to get a somewhat interesting groupoid from which you can define a reduced C-star algebra. And indeed, we observed very quickly that in fact, the reduced C-star algebra in this case is really just all continuous functions on G. This is a somewhat, I guess, unusual example in that G is already compact. Usually, you're dealing with things that are only locally compact. But in this case, G is actually compact. So you already have, just by looking at all continuous functions, they're already bounded, they're already compactly supported. So you don't need to do any kind of completion there. And we observe that this is really just another sort of form of the C-star algebra you get by looking at matrix valued functions, 2 by 2 matrix valued functions on complex projective space of dimension n. And that was relatively easy. And then we said, well, what if we switch things around a bit? What if we kind of twist things in the off diagonal direction? So we formed what we call these Peterson C-star algebras of order n. And they're pretty much the same, except we define these, the top left and top bottom diagonal entries. These are still complex numbers, just like before. But now these top right and bottom left entries in your matrix valued functions, we're now specifying that these are not complex numbers, but in fact vectors. So they're vectors which either lie or their conjugate lies within the point V. So V is a point of the complex projective space, but by definition, that is a one-dimensional subspace of complex space of dimension n plus 1, right? So we're actually specifying the entries lie in the subspace, which is the point, right? And these are all one-dimensional subspaces, so it looks very much like these continuous functions to M2. At least locally, that is exactly what it is. But globally, it's kind of different. And we were able to show that indeed, if you look at the resulting C-star algebra, you get something that really is different to continuous functions from CPN to M2. So we use this quite well-known classical result known as the Borsuk-Ulam theorem, which basically says there are no maps, no continuous maps at least, from some higher dimensional sphere onto a lower dimensional sphere, which preserve antipodal points. And so we did this proof by contradiction, where we said, if this was isomorphic to this, we could create such a map. Okay, therefore, the isomorphism does not exist. Okay, so to construct these kind of examples and other more sort of twisted examples. So this kind of non-isomorphism here indicates that PPN is some kind of twisted version of continuous functions from CPN to M2. So to construct these guys and a lot of other general examples, for example, coming from two cocycles, that's another way you can kind of twist the product in some sense. It's really instructive if you want to do this in a systematic way to look at what are called Fell bundles over Étale groupoids. And this is what I want to talk to you about today. So in particular, these bundles will include bundles formed in sort of a similar way here. So this A here will be a section of a certain Fell bundle. But to precisely describe what these Fell bundles are, it's going to take a bit of time. We're going to start from the basics and just look at, well, to begin with, just bundles. So what is a bundle? Well, officially, a bundle is really just another name for a map, right? So it's just an open continuous surjection from some space B onto another space X. So by this definition, you can see if you have an Étale groupoid, for example, G, then these source and range maps are indeed open continuous maps onto the unit space. So in that sense, these really are bundles over the unit space. And if you remember we talked about slices, sometimes these are called bisections, and that because they are indeed precisely the ranges of maps which are sort of sections with respect to both the source and range maps when you view them as a bundle. So this is not generally how you view Étale groupoids, but it suits the definition fine. Really, when we're looking at bundles, what we tend to do is we tend to sort of view them really not as maps, even though precisely speaking, this is exactly what they are. But we tend to view them or think of them rather as kind of collections of fibers. So the fiber is just simply the pre-image of some point, right? So you look at all these fibers and you sort of consider that the map row here is kind of gluing these fibers together in some way. And this is all just motivational, intuitional comments. Like in reality, P is just an open continuous surjection, but you kind of think of it in some way as gluing together all the fibers in a continuous and I guess open manner as well. And when we look at things in this perspective, we usually call B the total space of our bundle and X the base space of our bundle row. With bundles, another sort of the reason you often refer to bundles is it sort of indicates that you're really interested in the sections of the bundle. The sections are precisely, in precise terms, simply bright inverses. So another function f, this time from X to B, is a section of row if when you compose with row, you end up back with the identity. But again, really what you're doing or what you're really thinking about is you're thinking about these sections as if they're functions which choose an element from every fiber, and that's the function. So for every X, your f of X picks some elements of your fiber B of X. So these are sections, these are arbitrary sections, but of course we have a topology here. So really our primary interest in the end will actually be in continuous sections. And we'll eventually want to show that these continuous sections again form a C-star algebra, right? Just like when you were dealing with continuous complex value functions. Now they won't have complex values anymore. They'll take values in the fibers. However, as long as your bundle has enough additional structure, then you will be able to again define convolution and sums and everything, and it'll have a norm, and this will again get you a general kind of C-star algebra. Well, this will from starting from a Fell bundle, there will be a general construction in order to produce a corresponding Fell bundle C-star algebra, like the reduced and also the maximal, just like in the original case we looked at before. Our primary interest will again be the reduced though. But first we need to consider bundles, and in fact, first actually I want to just prove a little result that tells you why being open is important. You might think, why not just deal with continuous surjections? If you're really gluing the fibers together in some continuous way, then why does it matter that the map here is open as well? And there's various reasons why, but one immediate reason, one sort of nice little result you can prove when you have an open map, is that you can always lift convergent nets. This will be useful in a little result we prove later on. So more precisely, let's say we have some row now, which it could be a bundle, or actually at this point, I think it just has to be an open map. It doesn't even have to be continuous. So let's just take some open map, row from B to X onto X. And let's say we have some convergent net X lambda. And in fact, let's say it converges to something of the form row B. So it converges to something that, and we're picking an element B, if you like, within the fiber that it converges to. Then what we're claiming is that we can lift it in the sense that we have another net which converges to B now, such that when you project those B gammas now, so it could be a different index set, you project those onto the base space, then you get a subnet of X lambda. So you may not pull back X lambda itself, you'll pull back or you'll lift a kind of subnet of X lambda. But nevertheless, that will be all we'll need for most applications. So I hope you remember nets. I think this is one of the first things we were talking about when I was taking over from Karen like a couple of months ago. So remember, nets are just collections of things which are indexed by some directed set. So there's some ordering on the index set such that every pair has an upper bound. So to define the net we want, this B gamma, we first have to define the index set. And the index set is going to consist of pairs. So it's pairs where you have some open set, some open neighborhood of B, and some lambda in the original index set you were given, such that moreover, X lambda is indeed in the image of O under the map row. Right? So that's the set. The ordering now is basically the product ordering, where in the first term you just use the ordering you were already given, and in the second term you look at the reverse inclusion ordering. So for A to be below N, it's actually saying that O is a superset of N, or N is a subset of O. Right? So it's the opposite, it's the reverse. So that's our index set. And now first we want to show that this really is a valid directed set. So given two elements here in my new index set that I've created, I want to show I have some greater element in this ordering. And indeed I do, because you'll notice that, okay, if these are in the index set, then O is a neighborhood of B, N is a neighborhood of B. So their intersection is again an open neighborhood of B. Right? In particular, if I project the O intersection N onto the base space, oops, I then get, excuse me, I will get, particular something which is the same as row of B, right? I mean, row B is within the set, so this certainly contains row of B. And remember, the X lambdas converge to row of B. And if they converge, and this is an open set, this is an open map, so the whole thing is an open set, well, that means eventually I must be able to find some new here that lies within this image here. Right? So I can indeed pick some new such that X new lies within row of the image of O intersection N. So that's nice. That means it's above both of these two pairs here in this ordering I've just defined here. So we have a directed set, which is great. If you didn't have a directed set, then there's no way you could index something and get a net, right? So we've got our directed sets. How do we define the nets? Well, we have to pick some elements for each pair in the indexing set. So we pick something, we just pick any old B which lies within your set O here, right? With moreover the specification that indeed when you project this element you get X lambda. And we know this is always possible because our definition of the index set specified that X lambda has to be within the image of row of O, right? So there has to be at least some element B lambda O within O whose image is X lambda. So I can always do that. I can always pick such a net. Okay, and then basically by the way we've set everything up, by the definitions, it's now clear that B lambda O converges to B in the usual net theoretic sense. So that just means that I can always pick some element in the index set such that everything beyond that, every other element which is indexed by something beyond that, lies within some fixed open set. And indeed, if you're given some open set n, then you simply look at all the terms beyond mu n, and you will indeed find that by definition, b lambda O has to be an O, which by definition of the ordering has to be in fact included in n. Okay, so this really tells you that this converges to B. And also the last bit is to show that when you project this new net you have here onto the base space, that it is really a subnet of the net you started with. And indeed, all you do is if you look at the image here, you see this is x lambda, right? And so the fact that the map you get by projecting one index here just onto its first term, that this is definitely order preserving by the way we've defined the order here. And it's definitely it's surjective, in particular it's cofinal. And this is what tells you it really is a subnet of the original net x lambda, right? Okay, so that does everything we want it to do. Okay. So, what next? So, well, yeah, just a little side comment, I guess, is that you can actually show that this isn't just a one-way implication. It really does characterize open maps. Open maps are precisely those for which you can lift nets, or at least you can lift subnets from the base space to the total space. So yeah, I think that's the other direction is actually a little bit easier. But yeah, if you're interested, do that as a little exercise. So that tells you why openness is important in the definition of a bundle. But we want more structure. We'll need more structure to be able to find C-star algebras from the sections. And the first kind of thing we need will be some kind of norm or Banach space structure. So to define more precisely what a Banach bundle is, I have to just remind you what an upper semi-continuous map is. I mean, you could deal with continuous maps, but for these days, it's sort of well recognized that you want to be a bit more general to be able to get the most out of your Banach bundles. So just remember that an upper semi-continuous function is a map on any topological space X to the real numbers, satisfying this condition here. So that the f of the limit of any convergent net has to be greater than or equal to the lim sup of the corresponding value. Right? So when you look at the corresponding values here, if f was continuous, this would itself have a limit and it would be equal, right? Here we're not saying f x lambda it may not even have a limit, but it will have a limit supremum, right? So, and that will be, yeah, in some sense, a kind of upper limit, if you like, of these terms, and you're requiring that has to be below the value of f at the topological limit of this sequence. Whenever you have some convergent net. I mean, you can actually also view upper semi-continuity as continuity just with respect to a different topology on R. Instead of the usual interval topology on R, you would look at the topology generated by infinite half-open sets. Infinite half-open intervals, right? So you look at all the intervals which consists of from negative infinity to R, R, but not including R. And you can check this. This will define a basis for your topology. In fact, that will even define a topology. It's not just a basis. And upper semi-continuity really means continuity with respect to this much weaker topology on R. But that's just a sort of side comment. You don't need to worry about this. Maybe this explicit definition is probably more useful. Okay, so what's a Banach bundle? Well, it's a bundle. It's an open continuous surjection from some topological space B onto X, where moreover, we know that every fiber is a Banach space, a complex Banach space. For each particular scalar, we know that the map you get by taking any elements of the total space to scalar times that, right? Because we can do that because it's a Banach space. That this we want to be continuous. So this is sort of this is I guess many statements in one, right? Like there are many different scalars you could use, but it's saying each one of the maps you get is a continuous map on the total space B. We also want addition to be continuous, right? We can add within any fiber. We can't add elements from different fibers, but we can look at all the pairs which lie within the same fiber and clump them all together into a single set. And as long as this space here in the subspace topology, the subspace of the product topology, okay, as long as the map you get using addition from that to the real numbers, or sorry, not to the real numbers, to B itself. As long as that is continuous, then this is another condition that needs to be satisfied. And we also want the norm here to be upper semi-continuous. That's why I was worried about upper semi-continuity here. And last but not least, we want this kind of compatibility condition, or at least this is how I view it. It's sort of saying the topology on the bundle is, or the topology on the total space of the bundle is in some sense compatible with the norm structure. And it says something you would naturally expect, right? That it says that if I have some collection of elements in the total space, B lambda, some net, and if I project them to the base space, they approach some x. And if I further know that the norms of these B lambdas here, if they go down to 0, well, then as you would expect, B lambda has to approach 0x in the topology on B. And if the norms are getting smaller, of course, you would expect this to be true, right? But it doesn't follow automatically from the previous assumption. So this is something you have to state explicitly. And so there you have it. These are the defining properties of a Banach bundle. So there we'll meet some more examples, but just to give you maybe an immediate kind of trivial example, you can just take any topological space and then look at some Banach space B and just look at all the pairs, with B and X. So you just let rho here be the projection from pairs onto X, right? Just considering this in its usual product topology. Okay, and that will indeed give you a Banach bundle that's known as a trivial Banach bundle. Right? There's no real twisting here, if you like. And you can probably guess what the corresponding local version would be. So you'd say a bundle is locally trivial if I can cover the base space basically with open neighborhoods, such that when I restrict my bundle map rho here to fibers within that open set, then indeed it is isomorphic to a trivial bundle like of this form. Just because that's true locally does not necessarily mean it's globally trivial. This is something you might be familiar with if you've ever done some work in, I don't know, differential geometry, for example. So then you would look at manifolds, and then you would consider you would consider the tangent bundle or the cotangent bundle, and this will definitely give you a vector bundle, but it may not be trivial, or it may only be locally trivial. With our bundles, we're sort of going a bit further even. We're not even requiring local triviality. There's not necessarily any kind of fixed Banach space here I can use to get like local trivializations. Right? There could be, the fibers could be very different at different points. Right? All we're requiring is these conditions up here. But because of in some sense, because of the norm structure, then this allows us to even deal with this possibility that the fibers at different points can be very different. So what are some basic properties of our Banach bundles? Well, there's a few sort of obvious things that nevertheless need some kind of proof. So the first thing to note is that the subspace of topology on any fiber of your Banach bundle is in fact exactly the same as the norm topology. That's what you would hope anyway, right? This is what I guess what this compatibility condition is really encoding. That's what you hope it encodes anyway. So to see why, well, let's take some net here, which converges in the topology of the total space, right? So subspace, yeah. So let's say, and in fact, you could say that this is even holding in a fiber, I guess, right? So anyway, let's say that we have B lambda approaching B. Well, then it certainly follows that B lambda minus B approaches 0 lambda. Essentially, because you can imagine, well, you've got a net here. You could also consider the constant net with value minus B, right? Okay, and that will definitely approach minus B, right? But then you add the two nets together, and sum is continuous, so you're allowed to do that. That won't. You can then add the limits together as well, and adding B to minus B gets you 0 in that particular fiber row. And then you would notice that, well, okay, well, because of, yeah, that's right, because of this upper semi-continuity condition, the lim sup of these norms here has to be less than or equal to the norm of the limit. Okay, and the norm of 0 is 0, right? So this already tells you the lim sup has to be below 0, and And this is always positive, right? So that actually tells you the limit of these norm expressions is 0. So in other words, this is saying that B lambda approaches B in the norm topology. On the other hand, what happens if B lambda is approaching B in the norm topology? What if these norms do indeed approach 0? Well, then this is exactly what compatibility says. It says that, well, in that case, B lambda minus B has to approach 0. But if B lambda minus B approaches 0, well, you just, again, add B to both sides, and this is really saying B lambda approaches B. Okay. And so it's reassuring. But next, well, another thing to note is that scalar multiplication, we only required it to be continuous for a sort of a fixed scalar, but it turns out from our assumptions, actually, that scalar multiplication is jointly continuous, viewing this product in the usual product topology. So to see this, take some pair of nets now. So we take a net of complex numbers approaching some complex number Z, take a net of elements in the total space, B lambda approaching some element in B. Okay, now let's look at, well, firstly project down to the base space. So then you will see that, well, both of these, like the scalar multiplication doesn't change which fiber you're in, right? It's an operation on fibers. So this is lying within the fiber at rho of B lambda, as is this one here. Okay, and again, you're just doing operations within the fiber. So this really, again, lies within the fiber rho B lambda. Which we know approaches rho B, simply because rho has to be a continuous function. It's a bundle. Next, note that, well, if you look at the norms of these expressions, well, it's a Banach space, so you can take the scalars outside, and we know that this then has to approach 0. And there is something you have to observe first, and that is that the norms of these B lambdas have to be bounded. Again, this is this upper semi-continuity condition. You know that the lim sup of these B lambdas, because they actually have a limit B, that lim sup has to be less than or equal to the norm of B. And so it's maybe the whole thing is not bounded, but it's bounded beyond some point. So by restricting to a subsequence if necessary, a subnet if necessary, then you can really assume it's bounded. So if these are bounded, and if we know the Z lambdas approach Z, then this will approach 0. So something approaching 0 times some bounded net, okay, that's again going to approach 0. Okay, so, and then you go back and say, well, let's use our compatibility again. We know the norms go to 0. We know the projections onto the base, they approach some fixed element of the base, rho B. Therefore, the elements themselves have to approach the 0 in that particular fiber. This is exactly what compatibility says. And now we use the fact that, at least for some fixed Z, indeed, the map is continuous. And so in particular, ZB lambda does indeed approach ZB. And putting these two things together, noting that we can always add these two things together, these lie in the same fiber, and addition is continuous, so that has to be equal to the sum of the resulting limits. So in the end, this is saying Z lambda B lambda approaches ZB. And that's exactly joint continuity, right? You're taking some arbitrary net of pairs, Z lambda, B lambda, showing that their product does indeed approach ZB. So just a couple of little results that there are other little results too, I'm sure you could prove, but these are sort of two important ones I thought I should at least show you first. As we said, when we're looking at bundles, we're primarily interested in sections. So let's introduce some notation. Let's denote the sections of any bundle row here just by S of rho. Right? So it's all those elements, all those functions here from X to B, which are right inverses of rho, which end up picking elements in every fiber, basically. Now we can define the infinity norm, or the supremum norm, or the uniform norm, whatever you like to call it. Let's call it the infinity norm on these sections, just as you would expect by the supremum of all the norms of all the values that you have here, all those x's in your base space. Yeah. And I'm calling it a norm, but if I was really being sort of precise, some people get upset when you have norms which can take infinite values. So some people would instead call this an extended norm, because there is a chance that this supremum here could be infinite, right? These norms here, there's nothing to say this is bounded, right? I'm not assuming anything about A except that it picks some elements in every fiber. And those elements could increase depending on your function or your section A, right? So really, I mean, it's just something to keep in mind that when I say norm, I'm being a bit loose with the term and I'm allowing infinite values. But we can still talk about Cauchy completeness, even with these infinite valued norms. And the observation here to note is that sections are complete in the usual sense, right? Cauchy complete. Meaning that whenever I have some sequence now, so this is really indexed by natural numbers. I guess you could look at more general nets, but when you're dealing with norms and metrics, it suffices to look at sequences now. So if you look at some sequence of sections, and you assume it's Cauchy, that's really what this is saying here, then there is some limit. There exists some section A for which A approaches AN in the infinity norm, right? And it's really almost trivial. Once you look at it this way, you say, well, if these infinity norms are Cauchy, then in particular at each x, right, this is also Cauchy. The limit at a particular x is certainly going to be below the limit when you take the supremum over all points x, right? So that means that in particular in each fiber, again, you get a Cauchy sequence. Okay, and as each fiber is complete, we're assuming that every fiber is a Banach space, in particular it's complete. Well, then we can just simply let AX be that particular limit. Right? There's no need to, I guess, yeah, I guess I am assuming that things are housed off here. So maybe I haven't said this explicitly, but let's just assume, to make things easy, that the total space and the base space are always housed off. The reason being that makes limits uniquely defined. I guess I could get away with them not being housed off just by picking AX to be some limit. I mean, hang on, what am I saying? I guess in the fibers they're definitely housed. Banach space is definitely housed off. Okay, so in the fibers they're housed off, so the limit within the fiber, I guess, is unique. So here I don't even need it. Okay, but if you're worried about uniqueness of limits and that it's perfectly fine to assume everything is housed off. We will do this eventually anyway. Okay, so that's arbitrary sections, but really, like I said, if we have a bundle, if we already have this topology around, we want to use it. We want to actually deal with continuous sections, not arbitrary sections. So again, let's introduce some notation. Just like before, we had C of X to mean continuous complex valued functions on X. Let's just use C of rho here to mean continuous sections of a bundle rho. So the claim now is that these continuous sections are closed relative to this infinity norm. They're closed within this larger space of arbitrary sections. And that in itself, maybe we don't care so much about, but what we really do care about is that the continuous sections are also Cauchy complete. And this is an easy way of showing that, right? If we've already shown this is Cauchy complete, and we know that this is closed in some complete space, then closed subspaces again have to be complete. So why is this? Well, let's take some sequence again of continuous sections, and let's take some now arbitrary section, right? As long as if AN is Cauchy, we know such a section exists. But now we can just assume that we have some limit, right? Some limit in the infinity norm. The goal is to show that this limit is also a continuous section. Okay, so to show continuity, well, one way to do it is to take some arbitrary net in your base space, right, and show that the corresponding image, the corresponding the A here maps this net to another convergent net, which converges to A of X. Right, so let's take this particular sequence, and in fact, there's a sort of little trick. If you want to show what we really want to show is that A of X lambda approaches A of X, right? But instead of showing that directly for one particular net, it actually suffices to say that for every subnet, I can take a further subnet and show that converges. Right? That suffices to tell you the original net you had also converges to the same element. Okay. I just mentioned this because remember our lifting result only applied really to subnets. So if we're being super precise, we really have to talk about taking a subnet and then taking a further subnet, which you can actually lift. Okay, but once you've understood that, then we can just make things notationally easier and just assume that we have indeed lifted the original net. Right? I mean, if you're worried about this thing, then just write it down, and you can write it down more precisely in terms of subnets. But let's just assume that B lambda is indeed a lifting of this, right? So it's a lifting in the sense that B lambda approaches A of X, okay. However, and the corresponding projection onto the base space is exactly X lambda. It's exactly this net here. Okay, so then we do some simple calculations. So let's see. Let's take some epsilon above zero. This will we need to do this kind of temporarily just to get the result we want. So we know that AN approaches A with respect to the infinity norm. In particular, I can find at least one n such that AN and A are close with respect to the infinity norm, close like within epsilon of each other. So now let's look at the lim sup of these values here. So look at the image of X lambda under A and this B lambda we've obtained as a kind of lifting. Well, we know that A of X lambda is within epsilon of A n X lambda by this assumption up here. So we can replace that with this expression and just add an epsilon, right? This will not affect things. Okay, but then you say, well, what else do I know? I know that okay, so if this is true, okay, the norm is, that's right, the norm is upper semi-continuous, right? So I know that this does have a limit. Because AN is continuous, I don't know that A is continuous, but I know that AN is continuous. And I know that X lambda has a limit. So I know that AN X lambda does indeed approach AN X. And by assumption, B lambda approaches AX. So if that approaches that approaches that, multiplying by -1, that's continuous, taking the sum, that's also continuous, right? So I know this whole expression here approaches this whole expression here. Oops. So therefore, one of these conditions is that the norm is upper semi-continuous. So the norm of the limit has to be greater than or equal to the lim sup of the norms of the corresponding net. And well, we keep the epsilon around because we have to. And then we're sort of in business. We're again going to use this fact that A and AN have to be within epsilon of each other with respect to the infinity norm. Okay, so that means we can just replace that again with another epsilon. So we've shown that this whole expression here is below 2 epsilon. But now we can get rid of the epsilon because epsilon was arbitrary, right? We were looking at this expression here, okay, and the expression on the left here did not depend at all on our choice of n, right? So if I can do this for arbitrary epsilons, well then of course the only option is that this lim sup here had to be in fact 0. In other words, AX lambda has to approach B lambda, or this whole expression, AX lambda minus B lambda has to approach 0. I guess this should be, so this should be 0. So therefore, so then when you actually take away the norm, this is again compatibility. What this really means is that the actual values here have to approach 0 in the corresponding fiber, right? The limit fiber, if you like. So the 0 at the fiber X. And again, using the fact sums are continuous, this really does tell you that AX lambda approaches AX, as we already know that B lambda approaches AX. And that's exactly what we wanted to show, right? That is enough because we had some arbitrary net here. This is enough to show that A really is continuous. It really is a continuous section. So this will be important later on when we want to show that we have a C-star algebra. C-star algebras in particular have to be complete. So this will help us in that regard. And before moving on to some more interesting kinds of bundles, I want to talk about fullness of bundles. So a bundle is said to be full if for every point of the total space, you can find at least one continuous section which passes through that point. In other words, the value at that particular element of the base space of that fiber is indeed this element you started with, the total space. Yeah. And in practice, it's not hard to see actually that if you define a bundle, that if you're given some bundle already, that you can actually verify directly that it really is a full bundle. So non-full bundles are not even that common. But there is also a nice general result about full bundles, which I'd be remiss if I did not tell you about. So the interesting thing is that if your base space is locally compact and Hausdorff, then every Banach bundle is automatically full. And this is a little surprising at first, I think, because, like I said, we're not assuming any kind of local triviality at all. If you were assuming local triviality, then this would be pretty much immediate. But because we're not assuming any kind of local triviality, it is to some extent surprising that you can still always get these continuous sections passing through all these points. And this is a classic result of, yes, Soglio-Heroult, I think, Doherty and Hoffman. So I think Soglio-Heroult and Doherty, they proved it, assuming that the norm is continuous. But remember, we want to be able to deal with even upper semi-continuous norms. And I think Hoffman made some comment or observation to that effect, that you can basically do the same kind of proof, even when the norm is only upper semi-continuous. And in fact, these days, I recently was told about a sort of much better kind of modern reference for this result, because finding the actual proofs in the literature that they were originally given was not so easy. But there's a more recent paper where they prove some much more stronger results, which in particular imply this particular result for upper semi-continuous bundles or Banach bundles. In particular, you might view this in a sense as a very strong version of the lifting result we had before. That if you already know this is true, if you already know that your bundle is full, then it's very easy to prove the lifting result, right? Even without moving to subnets, right? Because say you had such a full Banach bundle, and you have some net x lambda approaching rho b. Well, then fullness allows you to just take some continuous section A, doesn't matter what it is, and then some passing through the point B, of course. So the value at A of rho B has to be B. So take some continuous section like so, and then the lifting you just find to be the values of this continuous section at each x lambda. And then it's, because A is continuous, it's immediate that this approaches A of rho B, which is then B. So it's a very strong lifting result, if you like. Okie dokie. I guess before moving on again, I want to make a brief note about compactly supported sections. So these were important before, remember, when we were defining the reduced groupoid C-star algebra. So they're also important here. So we look at, so we say a section, a continuous section is compactly supported if the closure of its support is compact. At least assuming the base space is Hausdorff, which I will do. So a corollary of this previous results of Soglio-Heroult, etc., is that if you have a Banach bundle and X is locally compact Hausdorff, then you could even witness this fullness with a compactly supported section. Right? So we have some compactly supported section passing through B. Okay, so the previous result basically yields this with some perhaps more general continuous section. And then you just note that Urson's lemma yields the sort of similar result in the sense that you get some scalar valued function now, some complex valued function Z now, whose value at a particular point, namely at rho of B, is just 1. And so then you just multiply these guys together, right? One of the results we proved a couple of slides ago, remember, is that scalar multiplication is jointly continuous. And once you know that, well, it tells you that the map from X to ZX AX is indeed continuous. And because at PB, this is just 1, so this takes the value A of rho B at B, right? So hang on, A of rho B, which is just B at 1. At rho B, sorry. Okay, so that will also be something useful that we'll need later on. And also a little observation here is that when you're dealing with compactly supported elements, our infinity norm here will indeed be a true norm, even in the more restrictive sense that it's always finite values, right? So again, this is, the fact that you have this upper semi-continuous function on a compact set, well, then it's bounded. But if it's compactly supported, then all the values outside the compact set are 0. So it's definitely bounded outside there as well. That's the idea. So at the moment we have these compactly supported continuous sections, and thanks to addition being continuous, we know we can add them. Thanks to scalar multiplication being continuous, we can have a scalar product. We have a nice norm now. So we have a norm space, right? Which is a good start. And in fact, I guess, yeah, it's not a Banach space, because even though we showed that continuous functions, continuous sections of rho, these are complete. We did not show that the compactly supported continuous sections are complete. And indeed, you wouldn't expect them to be, because you could take a trivial bundle. You could look at some function which vanishes infinity, which is still not compactly supported, and yet you can still approach it by compactly supported elements. So there's a good chance that this won't be complete. However, it will still be a norm space. Okay? And so this is a good start, right? This is the kind of thing we want to do, but we also wanted to have some kind of product structure. We wanted to be able to define a kind of convolution of these sections. But to have any chance of defining a product of sections, we also need a product between certain fibers. We need this extra product structure to be able to define the product structure on these sections. So how do we deal with that? Well, let's do a quick review of semigroupoids. So remember, in the lead up to defining groupoids, we very briefly mentioned what a semigroupoid is. And a semigroupoid is nothing other than just a set with some partial product defined on certain pairs, right? Associative in the sense that no matter which way you try and calculate a triple product, right, whether it's AB and then C, or whether it's A and then BC, right, that these should always either be both undefined or both defined and equal, basically. That's what associativity says in the partial context. Okay, a star semigroupoid. This is something we, I guess, haven't talked about, but a star semigroupoid is a semigroupoid with an additional involution, a map taking B to B star. And it's an involution in the sense that you do it twice and you just get back your original element B. And moreover, it reverses the order of multiplication. So it's an maybe an anti-homomorphism, some people might say. So the star of AB is just the same as B star A. Of course, when these products are defined. But what this says is that when the product is defined, the product of A and B is defined, then the product of B star A star is also defined, and it's equal to the star of AB. That's the long way of saying it. A topological star semigroupoid, as you would expect, it's a topology making all the relevant maps continuous. And here we have two maps. We have the involution on the whole of B, and we have the product defined on certain pairs, considered as a subspace of the product. Okay, so these two maps have to be continuous. Yeah. So it has to be, that's what you need to have a topological star semigroupoid. But we already know plenty of examples, namely Étale groupoids, right? If you have a groupoid, well, it's definitely a star semigroupoid where your star in this case is just given by the inverse. And if your groupoid is Étale, then all the relevant maps have to be continuous and also open. But here we only care about continuity. So in particular, this star, this inverse in this case, is definitely continuous. The product is continuous. So it's a topological star semigroupoid. And last but not least, I have to tell you what ISO code fibration is. It's a bit of a silly word, but don't blame me. I didn't make this up. This is, I think, at least a semi-standard term in category theory. So it's a map between semigroupoids such that the product of some pair in B is defined if and only if the resulting product in G is defined, right? And in which case you require, of course, the product to be preserved. So you require rho BC to be rho B, rho C. So if you're looking at functors between categories, well, forgetting about the units for the moment, a functor is something where the product in G is defined if the product in B is defined, basically, right? But here, an isocode-vibration, this is something stronger. It's saying that the product in B is defined also always when the corresponding product in G is defined. So we know they're equivalent. This slide strengthening will be important. If the star is also preserved, if the involution is also preserved, then you can talk about a star iso cofibration. So there's a lot of terms here, but they're all fairly straightforward, I think. Right? So hopefully that's self-explanatory. So now I can finally tell you what a Fell bundle is. These are the kinds of bundles we will need to be able to define C-star algebras from groupoids, even when you're introducing some kind of twist. So this definition goes back to Convergent in '98. I think there was another guy around about the same time, maybe even a bit earlier, who had a sort of similar notion of a sort of C-star algebraic bundle over a groupoid, but I'll follow Convergent more closely here. The Fell bundle is in particular a Banach bundle, but moreover, we want to have some compatible product structure on both B and G. So we want G to be an Étale groupoid, right? But we also want B to be a topological star semigroupoid, so kind of weaker structure. But B is still, in some sense, kind of controlled by G because we want rho to be a star iso cofibration. So preserving the product, preserving the star, and in particular, when the product, the pairs for which the product in B are defined are completely determined by the pairs in G for which the product is defined. So you have some B and C in your total space, you know that this product is defined only when you project down onto the base space, and you know that the source of one is the range of the other. We also want the product to be compatible with the Banach space structure, in particular with the additive and scalar structure, with the vector space structure. So we want the product to be bilinear whenever it's defined. Of course, sums of different fibers are not defined. Products of only certain pairs, only these pairs here are defined. Sometimes it's not defined. So to be more precise about what we mean by bilinearity here, what I'm really saying is that this map taking B to BC here is a linear map from this fiber to this fiber, where this fiber is it corresponds to any element G whose source is the same as the range unit of rho of C. So you're fixing C here and saying, well, look at a particular fiber B of G, which satisfies this condition, and then this map will always be defined, and you can say, and also the sums within the fiber will be defined, scalar products within the fiber will be defined. So you can talk about a linear map just for that particular fiber. And of course you want the other side. That's why you want, that's bilinearity, right? Submultiplicativity of the norm, whenever again it's defined. That's as you probably would expect. And the last condition is somewhat more C-star algebraic in flavor. So we want to have this C-star norm equality, but again, we're not dealing with an algebra here. So this is, well, I guess this product here is always defined, right? But the sort of interesting thing is, I guess, that the fiber in which B lies could be different to the fiber in which B star B lies. Okay? But we still require the C-star norm equality. And moreover, whenever we have some B here, we always want to be able to, in a sense, replace B with C, an element in a different fiber, within the fiber corresponding to the source of rho B, and yet still get exactly the same star product, if you like. Okay. So the last condition, I guess, is probably the least obvious. Why would you require these conditions? Well, one clue as to why you would require these is because you want at least the unit fibers. You want these guys to be C-star algebras. And indeed, this is basically what this says. If you have a unit, well, then any pair of elements in the corresponding fiber can indeed be multiplied. Okay, so they lie within B2, and the result will again be within BXX, will again be within exactly the same fiber. Okay, so these conditions, this condition 5 here applied within that fiber is really is the C-star norm equality in this case. Okay. And so what that really does tell you is BX is a C-star algebra. Okay. And once you know that the unit fibers are C-star algebras, well, then you can interpret perhaps this in a slightly better way. What this star condition here is really telling you is that whenever you take any product of the form B star B, then it has to give you some positive elements within the U-bit fiber. So positive in the usual C-star algebraic sense. Right? So it's not obvious, right? That you sort of think B star B should be positive, right? But if you're looking within that fiber, this is exactly what you need to show it. You need to find some element in this particular unit fiber, which again has the same star product, C star C. It's really, it's really to ensure the unit fibers are C-star algebras, but also in a sense to ensure that even the other fibers also have a little bit of a C-star algebraic character, if you like. Okay. How are we going? So what about some simple examples? Well, there's again a kind of trivial class of examples. Look at trivial Fell bundles, where you just take some fixed C-star algebra A, some fixed Étale groupoid G, and you look at their products in the usual product topology. And if you take your bundle map rho here to be just the projection onto G, right, then you can verify the axioms pretty easily and find out you get a Fell bundle, where the product is just the pointwise product, right? So if you have two elements G and H, such that their source and range match up, then you can multiply the corresponding pairs just by multiplying AB within your C-star algebra A. I guess I mean, you can probably guess what the involution should be as well, right? So the involution should send AG to the element A star G inverse. So yeah, that's something I guess I could have mentioned explicitly as well. But the more interesting thing, it includes examples like this somewhat interesting Peterson example we had before. I mean, the algebra itself is formed from sections of the bundle, but you can probably guess what the corresponding bundle is already from the definition we had of the Peterson algebra. So the corresponding bundle you need in this case, it's really a disjoint union of 4 separate bundles, each corresponding to these different entries in the 2x2 matrices, right? 0, 0, 0, 1, 1, 0. So the bundles corresponding to the top left and bottom right corner, well, these are just trivial bundles. They're just bundles over this groupoid here, CPN times times 0, 0, where the element of the total space is just some complex number. It's only for the off-diagonal terms. So here's a typo. So this should be 0, 1, not 0, 0. And likewise here, this should be 1, 0, not 0. Okay. So it's only the off-diagonal terms where you're specifying the elements of the total space to be vectors, right? Vectors in the points which are in the complex projective plane, or complex projective space of dimension n. So you take each of these has a natural topology, basically coming from the product topology, right? And then you just chuck them together, taking the disjoint union, and that gives you the bundle you need, right? And the Pn is again just the projection onto the last coordinate or coordinates. The product, well, when you have some complex number, it's just the usual scalar multiplication essentially. But when you want to look at the product between a fiber within this guy and a corresponding fiber in this guy, well, then you 0, 1, 1, 0. Then you have to use this dot product that we were dealing with before. Okay, so this does include the kind of motivating examples that we were really looking at before. So let's return to the general theory. So keep in mind we have some fixed Fell bundle over, let's say, a locally compact Hausdorff-Étale groupoid, just to make things easier. How do we define convolution? Well, we do it in exactly the same way as before, right? We have 2 sections. So these are just arbitrary sections of the moment. And you say the value at f is just the sum of these values at AJB of h, where the G's and H range over all groupoid elements whose product is f. The only problem is the problem we always have, and that is that it's not clear that this is always defined for some arbitrary sections A and B. So when I say something like AB is defined, what I'm really saying is that for every element of the groupoid, that the partial sums I get, right, by looking at some finite f here, which I'll describe in a bit more detail in a second, but these partial sums converge, right, in an appropriate sense. But again, what does that mean a bit more precisely? Well, I mean converge as a net. The net here is indexed by finite subsets of G, little g, big G. These are just finite subsets whose sources are always exactly the same as the source of little g. And the ordering here is just inclusion, right? Actual inclusion, not reverse inclusion like we were doing at some point before. This is actual inclusion. Okay, and convergence, so that's the net, and convergent is with respect to the norm topology. But as we know, this is exactly the same. In fact, it's the subspace topology of that fiber. That was one of the first elementary facts that we proved. Okay. Another way of looking at convergence in this setting is as unconditional convergence. So what this really means is that these terms in your series here, that they're non-zero for at most countably many elements. Right? If they weren't, then there would be no way to determine this sum. So they have to be non-zero for most countably many of them, and any way that we decide to enumerate them, the terms should again yield some convergent sum, and that the resulting sum, the resulting limit, should not depend on how we enumerated them at all. That's why it's unconditional convergence. It's perhaps not immediately obvious, but you can show that unconditional convergence is really the same as convergence in this setting here. But I think seeing it as convergence of a net of finite partial sums is perhaps more useful and more intuitive. Okay. Yeah, so we've defined convolution at least for some sections, not for all of them. Part of the theory will be about showing that for the sections we want to work with, so for the closure of the compactly supported sections, the convolution will indeed be well defined. But first, let's show something fairly basic. Let's show that this convolution is associative, at least when we restrict again to certain sections. So let's take three sections, A, B, C. Let's assume that at least the convolution of A and B is defined at every single point in our groupoid. Let's further assume that C is finitely supported. So there's only finitely many elements of the groupoid for which C takes some non-zero value. So in this somewhat restrictive situation, we claim that A, B, C is defined, as is A, B, C, and that these two products, no matter how you do the convolutions, in which order, you'll again get the same thing. Okay, proof. Well, first note that because sup C is finite and because AB is defined, then at least one of those triple products here is defined, namely ABC. Right? It sort of follows basically from what we already did, that if you define in convolution and at least one of the elements in your product is finite, then convolution is indeed well defined. Right? So more specifically, if you want to look at the value of ABC at some G, then you take this sum, but you only need to take the sum over those elements in the support of C. And there's only finitely many elements in them by assumption. Okay, but what is this really? Well, this AB of G H minus 1, we know it's defined by assumption, but what is it really? Well, it's a limit, remember, of these finite partial sums, like so. So where you're taking the limit of this subset here I'm using to basically denote finite subset of. And so where you take the sum over all these f's here, which by definition have to have the same source as G. So that means the particular F inverse G is indeed well defined. Okay, but you've got a finite sum of some nets which have a limit. And that's a basic result of analysis that means you can actually take the sum inside, that this is actually the same as the limit of that finite sum. And so we're just switching things around. Okay, but now what do we have here? Well, we just have two finite sums. And again, it's an elementary result that it doesn't matter, which way we do the finite sums. I mean, I guess that's really just, commutativity of addition, right? So we can really take the sum of little f within big F over here, and then put this sum over here. And once we do it that way, well, then we can even take AF here outside, right? This will then become constant with respect to this sum here. So we can take that outside. And now we're getting somewhere because, well, what's this sum here? Well, this is indeed just by definition, the convolution of BC at F inverse G. Right? If you look at the product of F inverse G, H inverse H for all these H's, it always gives you F inverse G. So this is really what this thing here is. And well, once you've done that, then you say, well, okay, this here is really just the convolution of A and BC. And from what, if you started with this, I guess it wouldn't be obvious that this sum converges, but we know that this thing up here does indeed converge. So this is just a different way of writing this. So indeed, this does converge. This product here, ABC, is actually defined at G and is equal to the thing we started with, ABC, G. So associativity holds, at least in some restrictive circumstance. And how much time have I got? So yeah, okay, 20 minutes. So I can start talking about module structure. So remember that one of the first things we observed is that all the unit fibers of some Fell bundle, they always form a C-star algebra. In general, the fibers definitely don't form a C-star algebra. Like there's no product within an arbitrary fiber. However, there is a product between an arbitrary fiber and the fiber corresponding to the range of G and the fiber corresponding to the source of G. So you can multiply this on the left and you'll still get an element of BG, or you can multiply any element of BG by some element of BSG on the right, and you'll again get an element of BG. And what that really tells you is that you have a module in the usual algebraic sense, a bimodule in fact, because you've got different things on the left and right. Yeah, this is just it's just rephrasing bilinearity in a sense. Because of the extra star structure we have when we have a Fell bundle, we actually have an even more special kind of bimodule, or an even more special kind of module, let's say. Because we also have this nice inner product. Okay, so given any two elements of BSG, we can always just take the star of one, and then we will, be able to multiply it by C. And we can use this to define an inner product. It's an inner product in the sense that it satisfies all the things you're familiar with from Hilbert space theory. Right? So if you switch the order of the pair here and take the inner product, right? That this is in fact exactly the same as taking the star of the resulting inner product. Moreover, there's the map from C to BC is linear, and so in the other term it will actually be conjugate linear because it's basically composing with the star. It's linear, and also it's also in a sense linear with respect to your the module structure. If you take some elements in BSG, the C-star algebra here, then you can either multiply that inside the inner product or you can multiply it outside the inner product. It doesn't change the result. And moreover, if these two elements are the same, then you'll always end up with something positive. And I mean positive here in BSG, right? So positive in the usual C-star algebra sense. And last but not least, it's positive definite in the sense that this inner product with itself is zero if and only if B itself is zero. I guess I should say B is zero. It should be zero in that particular fiber, right? So in the fiber B, it should be zero of G, right? So there's lots of zeros, right, in your bundle. I mean the particular zero in the fiber BG. And that's simply because of one of these conditions on our Fell bundle, right? The norm of B squared has to in fact be the same as the norm of B star B, which is just another way of writing the norm of the inner product B and B. This is one situation where this thing is useful. Remember the fact that this B here, it's not within a unit fiber, but it still has to satisfy this. And that allows you to say this really does have this positive definite property. And one of our assumptions was that BG is complete, that it's a Banach space, right? And so all of these conditions here, they tell you that what you really have is what's known as a Hilbert module. So it's a Hilbert BSG module. BSG is the C-star algebra. The Hilbert modules, they're exactly like Hilbert spaces, right? They satisfy all the same properties. It's just the value of your inner product is no longer just a complex number, but rather it's an element of some fixed C-star algebra. The same fixed C-star algebra that you can do right multiplication on. So they give you Hilbert modules, and there's some nice constructions on Hilbert modules you can do. And one that's important to us is taking sums. So you can always take some arbitrary collection of Hilbert modules with respect to the same C-star algebra, in this case BSG, and look at the corresponding sum. It's just like with Hilbert spaces, right? You have a usually countable collection, let's say, of Hilbert spaces. Then you just look at the sequences, which take values in all those different Hilbert spaces. And then to define your new inner product, you just take the sum of the individual inner products you started. Okay. So it's exactly the same here. You look at now. Well, you can look at sequences, or here I guess it's more convenient to look at sections which are supported in big G little g. So sections which are supported on all those elements, all those groupoid elements, which share a source with little g. Okay, and you don't want to look at arbitrary sequences because, well, then your inner product may not be well defined. So you specifically look at those sections here for which A star A X is defined. Right? So writing this more explicitly, A star A X, remember, is exactly the sum of these, A G star A G. Right? G is taken over all elements whose source is X. So here and that's more explicitly what the inner product is in this case. It's just the convolution of A star B at that particular element X. So I won't prove it. I mean, the fact that you get an inner product on, let's say, finitely supported sections, that is fairly immediate, right? Just verifying all of these properties for this new inner product, where you have finitely supported sections, is easy, because this is definitely well defined if you're dealing with finitely supported sections. The only slightly difficult thing to prove here is that the resulting Hilbert module you'll get is again complete. Okay, and if you're interested, you can go to what I think is quite a nice reference on these things. So this book by Rayburn and Williams, called Morita Equivalence and Continuous Trace C-star algebras. We won't really need the full strength of this result. All we will really need is the fact that that this forms an inner product when you restrict to finitely supported sections. The general result is good to know. Okay, so let's review the Cauchy-Schwarz inequality. This will again be useful to prove that our sections actually form a C-star algebra. So the classic Cauchy-Schwarz equality, remember, is something that applies to Hilbert space. Right? It says that when you have X, Y, in some Hilbert space, and you look at their inner product, then the absolute value of that is less than or equal to the product of the norms of X and Y. The norm being the usual 2 norm, right? This is the square root of X inner product with itself. So I think you must have seen this before. I think Karen must have mentioned this. Certainly, if we're talking about Hilbert space representations of C-star algebras, GNS construction, then at some point you really have to be familiar with Cauchy-Schwarz inequality. So I'm going to just assume that you know what this is. But what I won't assume you know is the fact that a similar kind of inequality holds, in fact, for Hilbert modules. You have to write things a bit differently now because remember, we're dealing with C-star algebra valued inner products, not complex values inner products. So the appropriate generalization in this case is to look at the product of these inner products, the product of these two operators, and you can show that this is below, in the usual C-star algebra ordering, this thing here. So it's the norm of the product of X with itself times the operator you get by taking the inner product of Y with itself. And to prove this, again, I'll follow this book of Rayburn Williams, which uses the following fairly elementary fact. So this fact is just that if you have a C-star algebra and you want to show that one self-adjoint, let's say element A, is below another self-adjoint element B, then it suffices to show that phi of A is always below phi B, where phi is a state. So you show this for all states, and then this is exactly the same as saying A is below B. And because it's a state, remember, these are just real numbers. These are just positive numbers. If A is positive, then this will be a positive number. So this sort of reduces the operator inequality to a collection of real inequalities, which can be useful. And the proof is, well, fairly elementary once you know about the GNS construction. Because once you know that, you can just take your abstract C-star algebra and assume that it's actually a concrete C-star algebra of operators on some Hilbert space. And then you simply note that the vectors always give rise to states, the unit vectors anyway, right? So this is generally known as a vector state, not too surprising. So for any x, this gives you a state. And so if you know that all the states satisfy this condition here, then this is exactly the same as saying that A is below B in the C-star algebra B of H. Again, I think Karen must have talked about this. There's various different, equivalent ways of formulating what A below B means. And one of the simplest, if you have a C-star algebra, a concrete C-star algebra of operators, is this condition here, that every vector state at A is going to be below every vector state at B. And that's within B of H, but again, the classic result says that the ordering, it doesn't matter whether you're dealing with B of H itself or with some subalgebra. The operator algebra ordering does not change at all. So this is what we'll really try to prove. We'll try and use this result in order to prove this result up here. So Cauchy-Schwarz inequality for Hilbert modules. How do we prove this? First, make a simple kind of observation about this particular equality here. So let's note that if I look at this expression here, right, this is the inner product of x and y. Now, so the inner product of that is a value of a, which I'm always allowed, remember, to multiply on the right by x, right? We're dealing with a module, so the value here can be multiplied by x. Okay, but I want to expand this in some sense. Well, so first what I do is I switch the order and I take the star, right? That's what equivalent, if you like. And then I know that I can always take any element of A here outside. So I do exactly that. And then taking the star, well, what does that do? Well, that switches the order of multiplication. So it's going to be xy star times yx star. But then xy star is just yx, right? And likewise, yx star is just xy. So this is what this reduces to. Right? This is, remember, one half of the key equality we want to actually prove. And a similar kind of calculation happens when you replace, the y here with xy again. So again, you can take the xy out the front and switch the order of operations. You can take this xy out the right-hand side, just leave it as is. And another classic operator algebra inequality is that whenever you have some element of a C-star algebra, in this case x comma x, and you multiply on the left by b star or on the right by b for any element b, right? Then indeed you can actually you can say, well, that's going to be below the norm times the unit operator, as long as one exists. If not unitized, doesn't matter. And you know that if something is below something else, well then then you get, well, then it's just a norm, so you can then just take it outside the front. So this is a standard again, kind of just imagine these as different elements of your C-star algebra. This is B star, this is A, this is B. Okay, you can always take the A out the front just by taking the norm instead. And now observe that the original Cauchy-Schwarz inequality does kind of apply to your Hilbert module by just taking any state and applying that to the result of x comma y. So phi is a state on A, x comma y is an inner product with value some element of A. The Cauchy-Schwarz tells us that the magnitude of that is below what okay, so you're basically saying you're basically looking at phi xy itself as some kind of inner product. It may not quite be an inner product in the sense that it may not be positive definite, but this is a minor issue in the sense you can always mod out by those x for which phi xx is 0. But okay, we can use this as we can pretend that basically it's an inner product, and then just apply Cauchy-Schwarz verbatim essentially to that. And here I've just done things slightly differently in that I've taken the square on the left, right? So usually the Cauchy-Schwarz would be stated as the magnitude of this is less than than the square root of this to give you the norm, and the square root of this phi y to again give you the norm of y with respect to this new inner product. Okay, but it's all equivalent. Again, if you don't believe me, just take a moment to sort of write down the details. And now we look at this inequality, except we replace this x now with x comma y. Well, then, thanks to these little calculations up there, we are hopefully going to get what we need. So make the replacement here. Well, first, I guess, look at phi of yxxy squared. Well, by this first calculation we did here, this yxxy is exactly the same as phi of xxy, right? And so this is the same as this. And we know that phi is positive, right? Yxxy is a positive operator. So phi of that positive operator is a positive number. So in fact, the magnitude thing here is actually a bit superfluous. But we can put it in if we want, just to get it into this form. Then we apply this inequality here, just with the appropriate replacements. And this is what we end up with. And again, this we already did some calculations to show that this is exactly the same as this up here. In fact, I guess I could have skipped this step here, because now what we really need to show is that this is below this, therefore this thing here is below this thing here. And now we're pretty much in business, right? I mean, it's looking a little complicated, but notice that I have a phi yxxy squared here, whereas over here I only have one phi yxxy. So I can just divide it out to get exactly what we need. I guess there's a slight issue in that, this could be 0 and then you're not allowed to divide out. But if it's 0, then this inequality is trivially true. This expression on the right here is always greater than or equal to 0. So you don't have to worry about the 0 case here. Okay, so this gives us this inequality, but remember phi was just some arbitrary state. And if you've done this for some arbitrary state, well, then you can say, well, this same equality holds for the corresponding operators. That was thanks to that little proposition we just proved there. So great, we've now proved the Cauchy-Schwarz inequality for Hilbert modules. The reason I want to introduce this is because I really want to actually prove a kind of Cauchy-Schwarz inequality for sections of Feld bundles at certain points anyway. So I think I have probably just enough time to outline this. So let's go back to the original case when you had some Feld bundle. A particular inequality I want to prove, which maybe looks a little scary at first, is the following. Say I have, just to make it easy, let's say I have finitely supported sections of my Feld bundle rho. Now fix some element of my groupoid G. So what I want to show is that the operator ABG, so when I take the convolution of AB and look at the value at G, which is AB, which is always well defined because I'm restricting to finitely supported elements, no problem. But if I look at that star times itself, then this gives me another operator in the fiber BSG, remember, and which is a C-star algebra, and I claim that operator is below this. So you take the norm of AB at G and the square root of this. So this is this is just a number here, but this is an operator. So you're taking the square root of this operator times some scalar, essentially. Proof. Okay, well, first write out what it means to be, well, this expression here. What does AB, G star AB mean? Well, let's write out convolution of ABG, but only for one of them. Right? So let's only do it for the right-hand side, let's say. And then you note that I can actually rewrite this as a kind of inner product, but where I put the dividing line, if you like, in between the AJ and the BK. Not between here as you might kind of expect, but I put it between here. Okay, and then it really is going to be an inner product where, on the one hand, you're looking at basically at B, but only its restriction to groupoid elements that share a source with little g. And on the other hand, you're looking at C, where C is this, again, element of this, infinite sum, if you like, which again, viewed as a section, is really the map which takes any H to A, GH inverse star, AB, G. I mean, that's combining this ABG star AJ here, except that I'm not using J. I'm replacing J, if you like, with GH inverse. Right? But because I'm taking sums, right, you're allowed to switch around these. You're allowed to sort of what's the word? You're allowed to do these kinds of replacements, right, without affecting the sum in the end. Okay, and now that I've written in this way, I can use this nice Cauchy-Schwarz inequality for Hilbert modules that we just proved. So we know that this operator here is less than or equal to norm of CC times this operator here. Okay, but this expression here, B restricted to GG, looking at the operator you get by just taking the inner product with itself. Well, this is really the first part of this expression here. It's really just the value of the convolution of B star B at the source unit of G. And likewise, if you again look at this expression C comma C, and here it's actually the norm of this that we're interested in. We'll write it out like this as this kind of awful looking sum, and then say, but hang on, G here is fixed. So really this ABG star on the left here and this ABG on the right here, I can really just take these outside. So I can really, using the norm again, of course. So this is really just norm of ABG squared times the norm of the sum of all these guys, taking the sum over these H's. But again, if you take the sum over these H's, then you'll see that this is really just the same thing as the convolution of A star A, but this time at the range of G, not the source of G. And then you have it. Again, using another elementary fact that in a C-star algebra, if you have two positive elements, one below the other, then the same applies to their canonical unique positive square roots. This is another classic fact. I'm not sure, I think Karen might have covered this when she was talking about unique square roots and positivity and things like this, right? So, but this is a well-known fact. The only thing to be careful of is that the reverse equality, the reverse implication does not hold for non-commutative C-star algebras. I think this is something I mentioned in one of my lectures, right? But that's fine. This direction is all we need. And that gives you what you want, right? So if you do these replacements, so BGG would be B star B SG, so that goes in there. This expression here, so ABG norm squared, this goes in here. And this is basically what this guy up here, AB G star, AB G, except you're squaring it essentially. So, but then when you take the square roots, then this thing up here is exactly what you end up with. And that's what we needed, right? So I think it's pretty good. I think this is all I planned for, and this is all I really have time for. But next week, what I want to do is I want to use this inequality to give us this to construct the C-star algebra we want, to actually look at continuous sections of certain, at least compactly supported guys, and even their closure with respect to a certain norm, and using a bit of calculations, using these kinds of results here, like this lemma, show that you really do get a C-star algebra. And this gives you a very flexible way of defining C-star algebras, like the Peterson algebras we were talking about before. And yeah, this gives you a more combinatorial, more bundle theoretic way of really analyzing a lot of interesting C-star algebras. So that's I think that's it for today. Are there any questions? Doesn't look like it, I guess. Nope. Okay, well, without further ado then, I'll hope to see you all next week. So hopefully next week, I will have some more details about the mini workshop I've been advertising before. Anyway, talk to you then.